So once again, welcome please. Today we will review some very common problems in rotation. As a matter of fact, please pay attention because these problems are very repetitive in the history of AP mechanics. Now, the very first example has to do with rolling motion. The next free response questions in the next exam will have to do with rolling motion. So pay attention to this. Now there are a couple of things. There are two types of rolling motion. But what do I mean? What is the definition of an object that is rolling? An object rolls if and only if it translates and rotates at the same time. You understand that, right? Rolling motion is a combination of rotation and translation simultaneously. Now, there are two types of rolling motion. You have rolling with slipping and rolling without slipping. Now, to distinguish between rolling with slipping and rolling without slipping, you just use one equation, but we are going to get to that. Now, keep in mind that as long as an object rolls, the total energy of the object is given by Ke rotational plus Ke translational, which will be equal to half mv squared plus half I omega squared. Now, when an object rolls without slipping, V is equal to R omega. That equation only applies if an object rolls without slipping, in which case the total kinetic energy will be given by half mv squared plus half beta mr squared dot v squared over r squared. This will give you 1/2 bracket 1 plus beta mv squared. Now, this is the total energy of the object. You could see that this is equal to 1 plus beta bracket kinetic energy translational. Now, the importance of this equation, this is the total energy of the object. The importance of this is really important. If you give an object, if an object rolls and an object slides, the rolling object has a greater total kinetic energy compared to the sliding object. Which means that if you push a box and a sphere up an inclined plane, the sphere is bound to go further because it starts first with a higher total energy. Therefore, it will end with a higher total potential energy. Now, this should synchronize with your thinking. Now, the next thing I would like for us to take a look at would be when an object rolls and slides. For example, for sliding or slipping, when an object slides or slips, the equations of motion that apply is Newton's second law for translation F equal to ma, which basically gives us m dv dt all equal to F net. We can all integrate this, and V final will be equal to V initial, the integral from 0 to t F over m dt. This is the equation that governs the motion of the object. In other words, the motion of the object will be governed by the kinematics equations of motion. Now, secondly, when an object rolls without slipping, what really does that mean? Now, I was grading a paper, I think it was Kyler's, and she underlined and she said she didn't understand what it meant by rolling and slipping. Now, I want to clarify that, I think. And it's a problem for a lot of people. Let me re-explain what it means when an object rolls without slipping. There are two conditions that must be fulfilled for an object to roll without slipping. Two. The first, A, the velocity at the point of contact with the surface is 0 at all times. So if you have an object like this, it is interesting when you look at it this way. If you have an object that is slipping, the entire object will, it doesn't matter where you are located, you will have one velocity. This is pure translation. But when an object just rolls and slips, it will spin at one spot. You understand that, right? Now, when that happens, can you ask your question, please?
I was coughing.
That's all right. It's natural. Now, look up, please. When an object rolls at one spot, like your car spinning in snow in the absence of friction, now the velocity at the upper rim is v/cm. The velocity at the lower rim, this is negative v/cm. And the velocity here is vertically downward. This is v/cm. And the velocity here is vertically upward. This is v/cm. Now, this is what happens incredibly when an object translates and rotates at the same time. What happens is we will vectorially add up these velocities. The velocity at the upper rim doubles because they are in the same direction. This is 2 v/cm. The velocity at what the lower rim cancels out. So there is the relative velocity at this point. The point in contact with the surface is 0. And at this point, the velocity will be at an angle of 45 degrees. So the point I want to make is the tires of a car, if you want to measure the velocity of the car by putting a measuring or speed measuring device on the tires, it will measure a slightly higher velocity than normal because the velocity at the upper rim is double the velocity of what? Of the car. You understand that, right? But the velocity at the point of contact with the surface is 0. Now, this is important because if it's 0, it means that the friction force that acts between the tire and the surface, even though the car is moving, is static friction. You understand that, right? So it's static friction that provides the torque that causes the tire to do what? Rotate, that propels the car forward. So without static friction, a car will what? Will spin, but will not go forward. Keep that in mind. Now, this also means something. Static friction cannot do work because it is the friction force that exists between two surfaces which are what? At rest relative to each other. Therefore, even though the car is moving, work cannot be lost by what? Static friction. So keep in mind that static friction cannot do work because it is the friction force that exists between two surfaces which are at rest relative to each other. Now, if that is the case, then note the following. 1. For an object to roll without slipping, the velocity at the point of contact with the surface is 0 at all times. And secondly, it is static friction that propels the object forward. Now, the example I wanted to do before going into all of this discussion is you have a sphere. You go to a bowling alley and you roll a sphere or a bowling ball, and it's rolling, and you are being asked to calculate the maximum acceleration the ball can have. Now we know that the sphere rolls forward. This is the velocity of the center of mass. The moment of inertia about the center of mass of a sphere is 2/5 mr squared. So if we draw the free body diagram for this object, it's kind of, now the question I want to ask is the friction force acting forward or backwards? It's acting backwards, because if the static friction force acts forward, it will produce a torque that will cause the object to spin counterclockwise and the car will move backwards. You understand that, right? So if the friction force acts forward, as many people might think, since it's the one causing the car to move forward, it will produce a torque that will cause the car to spin counterclockwise, which will instantly move backwards. So the friction force is acting backwards, that will cause a clockwise spin on the car. Now the radius here is r. That being said, we have the normal force N. By definition, static friction is always less than or equal to what? Mu s n. This implies that static friction max is equal to what? Mu s n. So we have here the torque causing the car to rotate in the clockwise direction is given by I alpha. This implies that F static max multiplied by R will be equal to what? 2/5. Now I'm going to use the generic form of the moment of inertia, which is just beta mr squared multiplied by alpha. And what is alpha? Alpha is A divided by R. This essentially implies that static friction max will be equal to beta m a square max. Sorry, not a square, a max. But what is static friction? Static friction is equal to what? Mu s n. And we know that n is equal to mg, which therefore implies that beta ma max will be equal to mu s mg. The m's cancel, and the acceleration, the maximum acceleration the object can have is mu sg divided by what? Beta. This gives you the acceleration that the object will have. Do you understand that? What do you realize? That the acceleration is inversely proportional. A is inversely proportional to what? Beta. The bigger the beta, the bigger the moment of inertia. Which means that if you roll two objects with the same moment of inertia, they will have this. If you give the two objects the same velocity, they will have what? They will move at the same pace. In other words, the bigger the moment of inertia, the smaller the acceleration. So if you put two objects on an inclined plane, the one with the smaller moment of inertia will have what? A bigger acceleration, and therefore will reach the bottom first. These are really some little minute conceptual stuff that you need to keep in your mind. Now, example 2. Yes, please.
On the other one you said.
Example 3 is we are going to redo a problem we did last semester. We have a block, and we have a pulley. This is M1, this is M2. The mass of the pulley is M. The moment of inertia of the pulley is beta mr squared. Now, this is a very common problem in the multiple choice section. They will draw a diagram like this. and asks you to identify a bunch of equations, which one is right and which one is wrong. To start first, we need to draw a free body diagram. We are assuming that all surfaces are smooth. This is M1G. That is N. This is T1, T1, T2, T2. This is M2G. We will consider the direction of motion to be positive. So if you draw the free body diagram for the first block, this will be T1, M1G, and for the pulley, T1, T2, for the hanging block, M2G, and the T2. Now, for the block, we will use the fact that the summation of F equal to MA to give the fact that T1 will be equal to M1A. For the pulley, we have T2R minus T1R, all of this equal to I alpha. This would mean that T2 minus T1 will be equal to beta mr squared multiplied by A divided by R squared, which will be equal to beta MA. So T2 minus T1 is equal to beta MA. That is the equation of motion for the pulley. For block 1, you have M2G minus T2 equal to M2A. This is the equation of motion for block 2. Now we need to solve for T1, T2, and A. To do that, we could use simple algebra, or you could basically add all the 3 equations. If you add all the 3 equations, you end up with equation 1 plus equation 2 plus equation 3 implies M2G should be equal to M1A plus beta MA plus M2A. This gives us A to be equal to M2G divided by M1 plus M2 plus beta M. And that is the acceleration of the object. T1 is equal to M1A, which is just going to be equal to M1 M2G divided by M1 plus M2 plus beta M. That expression gives us the expression for T1. Now, because of your intellectual curiosity, you could now calculate T2. Example 4. Example 4, this is similar to the AP question last year. We have an object initially horizontal. It's released from rest and it swings. Now, I'm going to make the problem interesting. I will deviate from how it works. This angle is theta. When the object reaches the minimum point, it collides with a putty and sticks to it, and both rises to a certain height. We need to calculate that height. This is an interesting problem. We are going to combine a lot of laws here. I just want to walk you through the process of analyzing problems in rotation. I'm going to use different methods to do the same problem so that you could see how each can be applied. So the rod is initially, which is uniform, is initially released from rest. in a horizontal position, let's call this position 1, such that the rod falls freely under the action of gravitation, or the force of gravity of the earth. Now we need to calculate, as a function of theta, the angular acceleration of the object. Now we can use two methods here. I'm going to start first method 1. Method 1, I'm going to use the conservation of energy. I will use the conservation of energy. Let us choose our, still in this case, I will use my I to be equal to beta ml squared. Just the generic I. But in the question, you will be asked to calculate I. So if we choose our reference point to be at point 1, this is the point where the gravitational potential energy is 0. Some of you may choose your reference point to be at this point. It really doesn't matter. But the only unique property is that any object below the reference point has a negative gravitational potential energy, and any object above it has a positive gravitational potential energy. So initially, the total energy initial will be equal to 0. The total energy final will be equal to what? mgh plus half mv squared plus half I omega squared. But the question is, what is h? I'm going to put a negative sign here because it's below the horizontal. Now, the force of gravity acts at the center of mass. This is mg. So that this distance from here to here is what we are actually looking for. This angle is what? Theta. So that distance is going to be L divided by 2, the sine of theta. So this means that the total energy final will be equal to negative mgl over 2 sine theta plus half mv squared plus half I omega squared. I'm moving on to the next slide. Therefore, we have negative mgl over 2 sine theta plus half mv squared plus half bracket beta ml squared multiplied by v squared divided by, what will be L? This will be L divided by 2. I'm going to do this all squared. All of this should be equal to 0. So if we simplify, you will immediately see that the m's are common throughout. We could take care of that. So we are left with negative g L over 2 sine theta plus half v squared plus, this will be 4 over 2. This should be 2 beta L squared divided by L squared. So the L's, I believe, will take care of each other. So this will be 2 beta v squared. All of this should be equal to 0. Our target here is to calculate v. We could multiply throughout by 2. If we do that, you will be left with gl sine theta plus v squared plus 4 beta v squared, all of this equal to what? 0. This would imply that v squared bracket 1 plus 4 beta should be equal to GL sine theta, and therefore the speed v will be equal to GL sine theta divided by 1 plus 4 beta square root. Now this is the speed of the object at an angle theta. This is the speed of the object at an angle theta. Now we have used the law of conservation of energy to arrive at this expression. We can also use Newton's third law to arrive at the same expression. But one thing I want to show you before I do that is the fact that at the bottom of the right, at the bottom, theta is equal to 90 degrees, and the sine of 90 degrees is 1. Therefore, V bottom will be equal to the square root of GL divided by 1 plus 4 beta. That is the value for V at the bottom just before collision. Keep this in mind. We're going to come back to this. Now let's use method 2. We are going to use the net torque model. The net torque model. We know that the summation of tau will be equal to what? I alpha. This implies that what is tau anyway? If we revisit our diagram, this is the pivot. The force is the force of gravity. This distance from here to here is the lever arm, which is just L over 2 cosine theta. If you agree with me, then you will have mg L over 2 cosine theta. All of this should be equal to I alpha, which means that mg L over 2 cosine theta will be equal to beta mr squared multiplied by alpha. The m's can take care of each other. And what do we know? We know that this would mean this would be L squared, not R squared. This would mean that alpha is equal to G cosine theta divided by 2 beta L. Am I correct? But what is alpha? Alpha is equal to d omega over dt, which is the same as omega d omega d theta. This implies that omega d omega is equal to g cosine theta 2 beta L d theta. And we are integrating from 0 to omega. We are integrating from 0 to what? To theta. And when you do your integration, you will end up with omega squared over 2. All of this equal to g bracket 2 beta L. What is the integral of cosine? Sine theta. So this is sine theta from 0 to what? To theta, which is the same as, which is g sine theta divided by 2 beta L. Are we missing something? Can you guys look at the limit and tell me what we are missing? What are we missing? Have you guys identified what is missing? Because I have. We have used the incorrect value for the moment of inertia. We need to use the parallel axis theorem to determine the moment of inertia about. Remember, I equal to beta ml squared is the moment of inertia about the center of mass. But our pivot is not about it's about the end. So it's going to be I will be beta ml squared plus m squared. So all you've got to do is replace this here and redo the work, and you'll get the same answer. This is a common mistake that you will make if you are not careful. How much time do we have left? Pardon? If it's 10 minutes, then I'm going to just skip straight and do these problems. Now we have an object. This is a uniform rod. Please neglect this part. It's not there. Just cut it out. This angle here is theta. The rod is of mass 3m. This is m. We need to calculate the tension in the string that will be able to sustain this system in equilibrium. Now we start first by doing our free body dike. This is 3 mg. You have the tension T in the string. If you remember that the pivot exerts a force like that, let's call that force R, which means it has an X component, Rx, and a Y component, Ry. That is the force the pivot exerts on the system. And this system is in equilibrium. That carries with it two implications. If the system is in equilibrium, it means that the sum of forces is equal to 0, and it means that the sum of torque is equal to what? 0. When these two conditions are met, we say that the object is in static equilibrium. We say that the object is in static equilibrium. This also means that we can resolve T into two components. You have here, this is T sine theta, this is T cosine theta. Now, the distance from here to here is the lever arm for the tension. So the first target is for us to calculate the tension in the string. And for us to calculate the tension in the string, we need to use the fact that the sum of torque about any point on the system will be what? 0. My advice for everybody here is, when you are calculating torques, choose your pivot to be at the point where most of the forces are located. The reason is because the torque of a force through the pivot is 0. So when you choose your pivot at the point where most of the forces are located, what happens? You simplify your problem automatically. So I'm going to pick my pivot to be at this point P. In which case, the summation of the torques about P will be equal to what? T multiplied by the lever arm, which is this distance, which will be L sine theta minus 3mg multiplied by the lever arm, which is L over 2 minus mg multiplied by the lever arm, which is L. All of this should be equal to 0. This means that TL sine theta minus 2 over 3 over 2 mgl minus mgl all equal to 0. Multiplying both sides by 2, you will have 2t sine theta minus 3 mg minus 2 mg all equal to 0. Therefore, t will be equal to 5 mg divided by 2 sine theta. This is the expression for the tension in the string. What will happen if the string curts? What will happen if the string curts? The beam or the stick will do what? Will rotate. And it will be the previous problem we just solved. If the string curts, the string will rotate and it will just turn and become the problem that we just solved. Now another common problem that you made in your homework was to calculate the force exerted by what? The hinge. And to do that, we use the fact that the summation of F equal to 0, which means that the sum of forces in the x direction is 0 and the sum of forces in the y direction is 0. In the x direction, the summation of Fx will be equal to Rx minus t cosine theta will be equal to 0. This means that Rx is equal to t cosine of theta, which will be equal to 5 mg divided by 2 cotangent of what? Theta. Similarly, we know that the summation of Fy is equal to 0, which means that Ry will be equal to 4 Ry, let me erase that. This means that Ry plus t sine theta will be equal to 4 mg. Therefore, Ry will be equal to 4 mg minus, if you put in t there, the signs will cancel. You will have 5 mg all divided by 2, and you can simplify, which will be 3 mg over 2. That is the force in the y direction. That is the force in the y direction. When you go home, look at page 962 and review the work example on 962. Very important. Review the work example on 962 and do 964.